terms of the volume of an atom, and I know that if you use the electron cloud as like the edge of the atom, not all electron clouds are spherical, because actually we talked about S-type are spherical, P-type are dumbbell, F and D have sort of different kind of crazy things, but in general, have a spherical region that your electrons are supposed to be confined to. The volume of the sphere is this, where you take the radius, you cube it, take it times par 4/3 pi. Okay, so that's how we calculate the volume of an atom. But I want to just narrow our discussion to the main group elements, and this is where I'm hoping that Monday's, it's not a review, but I'm hoping that Monday's kind of lab, rehash of the periodic table lab will kind of remind us all how we chunk up the periodic table. We talk about main group elements, those are your A group elements. So that'd be these two groups and these 6 groups. Those are our main group elements. We do have a trend in size. So that arrow going down is saying it increases as you go down the period. And to me, that's like, oh yeah, Mrs. Snipes, I totally got that. So calcium versus strontium is bigger than calcium. This one is a little less intuitive, and at the end of this lecture, I'm going to try to tell you why it works this way. But if I kind of let's pick on, for instance, this trend as we go from argon back to aluminum, actually it gets bigger. Aluminum is bigger than chlorine and argon. You have to wait. It's got 13 protons and 13 electrons. How can it be bigger than 18 protons and 18 electrons? I have to kind of convince you of that, but it is. Atomic size. And I've limited just to the main group elements. Okay. So what I took out were these group B elements, what we call transition elements, transition metals, and the intertransition metals, transition elements. So here we go. This is group 1A. Okay, they're getting larger. Group 2A getting larger. 3A. And again, and I'll tell you in a minute why I'm pulling the B's, but make sure we're all on the same page here. I could take the column 1A, I could put a split right here, and we talked about this, was it just Wednesday, that these are our S block, okay? These are our S block, these guys, and these guys are our P block, which isn't my point here, just to kind of link in something else we were talking about. Oh, I can't spell block. You know what I mean, P block elements. But then do you see the trend that I said just a minute ago? Oh, sorry, we have one more group. Rare gases. The trend I said, and I picked on argon, that period 3. And so as I go back from right back to left again, its size increases. It's just as I said. I don't know that much of a mystery, but we'll touch on that coming down. And you don't need to be able to explain it to me, what I'm going to tell you at the end of the period, why it increases as you go from right back to left again, why atomic size increases as you're like decreasing atomic number, but you need to know that that is the case. This is showing you, again, the group A elements, and the number there actually is the radius of an atom of that type of element, neutral atom, and the units are in picometers, and pico is 10 to the negative 12. So I do have this video. It's not a great video as videos go, but it's not bad.
The radius of a single chlorine atom is defined as 100 picometers, which is half the distance between the centers of the atoms in a Cl2 molecule.
No. And we talked about there are 7 elements that are diatomic elements, the Hoffer-Nickel, hydrogen, oxygen, fluorine, bromine, nitrogen, iodine, chlorine, and that's it. So this makes sense. So all they're doing is atoms are very small. So in order to get, to wrangle it, so you got a radius, which is from the nucleus out to the edge of the electron cloud. That's a tricky thing. So this is diatomic. This is a Cl2 molecule. We can get the distance between the 2 nuclei and then note that half of that would be the radius. That would be where the electron clouds of one is bumping up to the electron cloud of another. I'll buy that. And then similarly, this slide looks at coming up with atomic radii of carbon and chlorine. It's just where do those numbers come from? And again, it's not like you're measuring the distance of the length of a table. Okay. So like I said, the trend going down a group, okay, is you know, you're adding on a bucket load of electrons. I don't know, I can't remember who I picked on, like calcium versus strontium. Okay, you're adding on what, 18? If they're both neutral, you're adding on 18 more electrons. So wow. But the other thing is, we talked briefly, and I might hit this a little bit on Monday, but we said that you can come up with electron configurations just looking at where they are in the periodic table. We would say, for instance, calcium, if I go back to the rare gas notation beyond argon, we have 2 electrons, and they're actually 4s2. So this would be argon, yeah, argon 4s2. Okay, strontium would be krypton 5s2. My point here is that we actually have, like the slide says, a higher N. Okay, instead of 4s2 valence electrons, we have 5s2 valence electrons. So the other thing then, the trend of increasing atomic size from right back to left again. Okay, it's a little more interesting. Okay. This says the trend of size decreasing going from left to right. Let's see, decreasing going from left to right. That's the same thing as increasing going from right to left. Okay, so hopefully we're on the same page there. I'm going to talk a little bit about this idea of what holds, we're going to have to remember what holds an atom together, kind of general structure of an atom. And we're going to talk about attractive and repulsive forces and how that gives the atom a particular volume. Okay. So as I draw an atom up here, remember that like charges repel like charges. So the attractive forces that, and it's the what the electrons are going to do, that's going to actually give the volume of the atom. So I'll go ahead and draw a lithium atom. I'll give it 3 neutrons. I'll give it 3 electrons. Okay. So here's the deal. When it's talking about attractive forces, that would be this here from the negatively charged electrons, all 3 of them, into the positively charged nucleus. That's attractive. The repulsive forces then, to give it volume, okay, would be the electrons repulsing each other. Okay, so this actually, this is repulsive, and this is attractive. That's why I've kind of drawn that with 2 arrows and that with just 1 arrow. That's kind of what's going on within an atom. And so with regard to volume, you figure as this attractive forces increase, it's going to make the atom smaller. So if these increase, smaller atom. And if the repulsive forces increase, larger atom, right? Increase, larger atom. Makes sense. I like things that make sense. Okay. So then at the crux, and again, I'm going to kind of introduce something called effective nuclear charge here at the end of this part to show you why this is the case. But so as you go from one element to the next element in along the same period, okay, that must mean that, coming up. So let's go from left to right again in the periodic table in the same period. We know that it's arranged so that we're increasing atomic number, okay, increasing atomic number. So we're increasing the number of protons in the nucleus. Okay, number of protons, if you increase the ultimate charge of the number of protons in the nucleus, then you would expect then the electrons to be drawn closer to them. Okay, so that makes that is increasing the attractive force. Okay. As again, we go from left to right, increasing atomic number. As long as those atoms are neutral, we're increasing electrons. As we increase electrons, we should increase the repulsive forces. So the fact that as we go from left to right, increasing the number of protons, increasing the atomic number, that suggests that actually it's the attractive forces that are kicking in from left to right along the same period. Okay, since the atomic size decreases from left to right, the attractive forces are kicking in more than the repulsive forces. So hold that thought. In the meantime, you could be faced on your test with a question about relative size, as long as the atoms are neutral. We could pick on this set of 5 elements, and we should come up with who's going to be largest, who's going to be smallest. And my solution coming up is to find them on the periodic table, and that's totally what we're going to do. So if we locate these 5 on the periodic table, here they are. All right. So a little bit of, hopefully a little bit of logic kicks in. Notice as we go down a whole nother period, they get larger. So right away, can you see where the largest one's going to be CS?
Did we skip a page?
Did we skip a page?
Yeah.
Did we skip a page?
This is an example. Oh, okay.
Yeah, I did these 2. So yeah, I didn't say very long these 2, but those 5 are. Yep. So fluorine's going to be smallest, cesium's going to be largest, and you're right. And I guess we just had a little bit of wrangling. And calcium, to me, calcium's, even though it's to the, what I say, I can't get my left and right mixed up. Even it's over here to the left, it's still going to be larger than phosphorus and sulfur. Okay? But phosphorus and sulfur, how many people think that, I'm going to ask larger or smaller. I'll start with phosphorus. How many, and I'll go smaller. How many people think that, think of the answer, phosphorus would be smaller? How many people think sulfur? How many people think that phosphorus would be larger than sulfur? So that's kind of how you deduce that. I think I have some arrows to kind of show you. Smallest would be fluorine, largest would be cesium. And as you said, phosphorus is going to be larger than sulfur. So sulfur, then phosphorus, then we'll pick up calcium, and then we'll pick up cesium. Okay. So that's how that goes. All right. And by the way, in terms of picometers, here are their relative atomic sizes. So this would be from the nucleus, the radius, out to the edge of the electron diode. Okay. So when I did the comparison, I basically set aside the group B elements, the transition and the intertransition metals. Remember that the intertransition metals are sometimes called the lanthanides and the actinide series, because they're, it's not as clear cut, the trend. These are the, well, so see the 1A, 2A, and now we have 3B through 2B. So starting here, this third column, you can see that we definitely still have the relative sizes in terms of jumping down a period, but across the period, we kind of have some things they don't behave as well. So I mentioned effective nuclear charge, and actually I have a little folder here that I pull out with regard to effective nuclear charge. And I'm going to write the formula on the board because my pen does not write very well here. Effective nuclear charge is, the symbol is Z star, and you can actually calculate effective nuclear charge. We're going to take, for any atom, you would take the number of protons in the nucleus, and from that you would subtract, and I'll try to kind of remind you, we did talk about what this would be. All electrons are not created equal. You're going to subtract from the number of protons the number of inner electrons. Inner electrons, i.e. Non-valence electrons. Okay, remember, valence electrons are the highest N. Okay, non-valence electrons. Sometimes these are called, these inner or non-valence electrons, sometimes they are called shielding. They have a shielding effect. Shielding electrons. Okay. So I'll kind of show you what that looks like, and then I'll kind of finish up with my slides. If I pick on magnesium and phosphorus, and the reason I'm doing that is to try to show the point that they're in the same period. So how many think magnesium would be the smallest? How many think magnesium, phosphorus, magnesium would be the largest? And you're right. So let's kind of show you, according to the effective nuclear charge, what that would look like. We pick on magnesium over here, a magnesium atom, its atomic number 12, so it's going to have 12 protons in its nucleus. And we talked about finding homes for the 12 electrons, and they would look like this. The first 2 electrons would go here in the 1s subshell, so 1s2. The next 2 electrons would go here, 2s2, and then they go here to the 2p, excuse me, and I need 6 electrons, so I'm up to what, 10? That's like neon. And then I need 2 more, so they're going to actually go in the 3s2. So that's how those 12 electrons around a magnesium atom are configured. According to my little formula up here, I can come up with the effective nuclear charge of that nucleus. This is my nucleus, like this. I have 12 protons, and from that I am going to subtract the inner or the non-valence electrons. All right? So inner or non-valence. These are valence, right? So these must be inner. And here in a minute, I'm going to say that these are actually shielding, effectively shielding these valence electrons from the positively charged nucleus. So anyway, so I get what, 10 inner electrons minus 10. I'm getting an effective nuclear charge of +2. So what that means is +2. What that means is when these 2 electrons go, these valence electrons go to give a volume to this atom, each one of them, this is how I think of it, are independently having a pull of +2. So here we go, hold that thought. All right, we're going to do a similar analogous thing with phosphorus. The element phosphorus is atomic number 15, so it's going to have 15 protons in its nucleus. The electrons are kind of configured similarly. We have 2 electrons in the 1s, we have 2 electrons in the 2s, we have 6 electrons in the 2p, and then we go through 2 electrons in the 3s, and that brings us to 12. I need 3 more. So I'm going to have to move on to my 3p, and I'm going to 3p3. So these are my inner electrons. I have 10 non-valence electrons, and I've got 2 plus 3. I've got 5 valence electrons. Exciting times. So here we go. Here are my 2. Here are my 3. And I know they aren't going to be clustered like that, but think of those 5 electrons out there. The effective nuclear charge of the nucleus.
My website is fast. How fast?
The effective nuclear charge of the nucleus is going to be the number of protons. We have 15 protons. And from that, we're going to subtract the non-valence electrons. These are the shielding electrons. So minus 10. I got a plus 5. So in other words, the effective nuclear charge, is a plus 5. So when I go to show the relative, when I go to show each one of these guys being pulled into a plus 5, I'm going to actually kind of do it like this. That's my attractive force. When I go to show each one of these guys being pulled into a plus 2, I mean, oh, not so much. So what I've tried to do is to kind of show relative arrows here. Okay, so these guys are pulled a lot. The attractive forces is a lot more than these guys. So that makes these guys, that makes the overall atom smaller.
So why is there 2 sets of valence ones on that one?
Because they have to be in different subshells because the S can only accommodate 2 electrons, and we go on to the P. So 3s2, 3p3.
So it wasn't just the 3p, but then this one thing.
Because they're both n is equal to 3, so it's collectively that's the highest n. Yeah, and your subshells or your valence electrons can be in more than one subshell. So that's what my slides do. To summarize, electrons in the lower n, non-valence electrons, basically shield the electrons, the valence electrons, from the nucleus. And that's how you kind of come up with that effective nuclear charge formula. So, yeah. So anyway, I thought kind of anticlimactic. So this assignment is due on when we meet again on Monday. Shouldn't be too hard of one.
So is it like the higher the charge, the smaller it is?
The higher, and this isn't necessarily a charge, it's an effective nuclear charge.
Yeah, that's what I mean.
Yeah, the higher the effective nuclear charge, the smaller it is.
Okay.
And if you're in the same period, going across the period for the group, or excuse me, for the main group elements, group A elements anyway, you're going to see that this take over, and that's why it gets small as you go across. That's all I have for today. Didn't we get out early on Wednesday too? So yeah, we're out early again. Monday we'll do the periodic table. So I was telling them, if you think of it Monday, bring your lab thing too. So we're gonna kind of figure out that lab and maybe test on Tuesday.